nuclear donut for Elon Musk, or the engine that will deliver a mission to Mars. To figure out how to populate Mars, you need to have the mind of Einstein, the wit of Louis C.K., and the courage of Captain Jack Sparrow. The inefficiency of rocket engines still remains the main obstacle. Chemical propulsion systems are capable of developing high thrust, but they have a small specific impulse. In other words, they cannot maintain traction for a long time due to the rapid fuel consumption. It's one thing to go into orbit, it's quite another thing to make an interplanetary flight. There is nowhere to refuel in outer space. A few words about the unusual approach of Musk's company. This is really interesting. Usually, computer simulations are carried out before launches, and only after that, prototypes are tested. NASA doesn't like explosions. Musk has a different approach. SpaceX produces prototypes of varying levels of readiness with the MK and SN indexes for testing specific technologies. For example, Starship SN2 was created to test the structure to which the engines are attached, and the SN5 was launched with one Raptor SN27 engine, but without the fairing. This explains the unfinished appearance of the rocket, but the SN10 had 3 engines. Things NASA tried to hide from the public eye were turned into a show by Musk. We are talking about the interplanetary transport system. In-orbit refueling is a key element of this system. The algorithm resembles a computer strategy game. The first rocket launches a ship with people into orbit. The next to go are tankers with fuel. After refueling in orbit, the Starship will be able to go on an interplanetary flight. Science fiction is getting closer to reality, but if a new type of propulsion system appears, then Musk's idea loses all meaning. While physicists were thinking about creating a propulsion system, NASA developed a strategy for the development of the red planet. The plan of a person's stay on Mars from the first day until the opportunity to have visitors there is developed in sufficient detail. In general, the colonization strategy looks like this. The first ship delivers a 3D printer to Mars. At the next stage, the 3D printer creates the individual elements and components of the future stationary engineering structure. The building materials are soil, water, rocks, and atmospheric gases. One of the tasks of the Perseverance rover is to collect samples of everything on Mars. After that, the printed parts are assembled in the correct order, and voila! We have a full-fledged Martian base, capable of receiving people and cargo from Earth. That's what we meant when we talked about WIT, delivering a small 3D printer that will print a bigger 3D printer, and so on. But seriously, 3D printers have already been successfully tested on Earth and aboard the ISS. Experiments have shown that these devices are capable of printing almost everything that is necessary for the life of colonists on Mars. This will be more efficient and cheaper than delivering everything needed by space shuttles. The only difficulties are energy sources of appropriate capacity, and these, as you might guess, are the main component for the life support of the base. By the way, a 3D printer also needs energy. It turns out that our civilization has no alternative to nuclear power units. The 3 most common concepts of a nuclear rocket engine were known until recently: solid phase, gas phase, and liquid phase. Each type corresponds to the aggregate state of nuclear fuel: solid, melt, and high-temperature gas or plasma as its alternative. A solid-phase nuclear rocket engine is essentially a nuclear reactor, or a chamber where a nuclear reaction takes place. The fuel element is rods or hollow tubes. Uranium dioxide pellets sealed inside each rod are the fuel. This is how most stationary nuclear reactors work. The nuclear reaction of uranium dioxide heats the rods, which in turn heat the medium, or, as nuclear physicists say, the working medium of the reactor. Hydrogen is usually considered a working medium for a solid-phase nuclear rocket engine. Less commonly, it's ammonia or helium. Let us recall that water vapor from heavy water is the working medium in nuclear reactors on Earth. Compactness is important for a nuclear rocket engine, so hydrogen is acceptable. Turning into gas, the working medium breaks out into the nozzle, and thrust appears. The specific impulse of a solid-phase nuclear rocket engine is 3 times higher than that of chemical rocket power plants, and is about 800 to 900 meters per second. For example, SpaceX's Raptor engine used for the Starship has a specific impulse of 380 in vacuum and 330 at ground. For liquid-phase jet engines, where nuclear fuel is in a liquid state, the impulse is 14,000 meters per second. In a gas phase or plasma nuclear jet engine, the impulse is even higher, 30,000 meters per second, which is 10 times more than that of chemical analogs. However, working models of nuclear jet engines do not exist, neither in the United States nor in Russia. Spacecraft are still powered by chemical propulsion systems. For example, Elon Musk's SpaceX Starship uses a mixture of liquefied methane and oxygen as an oxidizer. It is not surprising, because the coolant itself, or the working medium, flies out of the nozzle of a nuclear power plant. The danger of the exhaust is obvious. Radioactive gases are breaking out. Now, if we could only find a way and create such a cycle so that a thermonuclear reaction would be safe both for the environment and for the astronauts, it would be a real revolution. Fatima Ebrahimi, a physicist at the Princeton Plasma Physics Laboratory, PPPL, of DOE, recently unveiled a new concept for a propulsion system that could quickly deliver a spacecraft to Mars. The journey will only take 3 months. That's incredible. In fact, there is such a reactor at Princeton. Observing its work led Fatima Ebrahimi to think about a nuclear rocket engine, the effectiveness of which would allow us to talk about a mission to Mars as a real event. We're talking about the tokamak reactor, a toroidal vacuum chamber with magnetic coils that contain and control high-temperature plasma inside the reactor using a magnetic field. By the same principle, the plasma on the Sun is constrained by powerful magnetic fields. The tokamak reactor looks like a donut, only it's almost hollow inside. If you bought this one at Dunkin' Donuts, you would be unhappy. Plasma plays the role of the filling. The particles are accelerated up to a speed of 20,000 meters per second in a circle inside the reactor, and the plasma takes the form of a closed cord. If you open the torus and let the energy out, you get a tremendous thrust and, most importantly, effective braking. Because accelerating to crazy speed is only half the battle, it is also important to brake at the right time. According to Fatima Ebrahimi, a spacecraft with an engine like this will reach Mars in about 3 months. It's not a big deal compared to previous performance that was possible with chemical rocket engines. But how can it be applied to a rocket? The peculiarity of tokamaks is related to the fact that the larger the donut, the more stable it works. The idea of tokamak was formulated for the first time by the Soviet physicist Oleg Lavrentiev in the middle of the 50s of the last century. At the time, this technology was actively developed by the United States, Soviets, China, Japan, and South Korea. Depending on the strength of the magnetic field, the plasma either slows down or accelerates in the system. The density of the plasma depends on the strength of the magnetic field. Similar phenomena can be observed on the Sun. Theoretically, plasma in tokamak can be heated up to 150 million degrees. By comparison, the temperature in the hottest part of the Sun, in its core, is about 15 million degrees. The problem is its poor stability, and the smaller the size of the tokamak, the more the unstable behavior of the plasma is manifested. As soon as the plasma touches the reactor wall, it immediately loses energy and destroys the reactor walls. The world record for holding high-temperature plasma was set at the South Korean K-Star tokamak in 2016. The scientists heated the plasma to 50 million degrees and held it in a magnetic field for over 70 seconds. Then, the plasma lost its shape and touched the wall of the tokamak, turning it into steam. The reaction stopped. As you can see, the technology is still imperfect, even in a terrestrial laboratory. How can it be implemented in a flying object? The nuclear rocket engine is relatively compact. How nuclear physicists are going to tame plasma in such a reactor is a big question. If the engine collapses, then the fate of the astronauts will be not so enviable. So far, Princeton scientists have figured out how to protect the walls of the tokamak from destruction. It turned out that boron copes with this better than other coatings. The material is very poisonous though, and the reactor has to be stopped and serviced after each break of plasma. When this happens, all laboratory workers are evacuated to another room. There is also a more efficient and safer way of covering the chamber walls with boron, which also does not require stopping the tokamak. The boron powder is injected directly during the operation of the reactor. Test leader Robert Lunsford from the U.S. Department of Energy's Princeton Plasma Physics Laboratory believes that this technology is more effective and less dangerous. Let's assume that the tokamak can be saved from destruction and, if necessary, restarted right in outer space. How do we achieve plasma stability? There is a theory that plasma behaves more stable in vacuum. If a thermonuclear rocket engine is working only in outer space, then the wall can be removed from the structure, leaving only small protective pads on the magnetic coils. This will facilitate the task of igniting a thermonuclear plasma. Perhaps Fatima Ebrahimi thought about this when she watched the tokamak in her laboratory. If so, we will soon see the engine depicted by the futurists on the UFO. Then the power plant of the spacecraft must consist of different types of rocket engines. For example, a traditional chemical engine will launch a rocket into outer space, and a nuclear installation will start in outer space. There is also the problem of choosing a suitable working medium and a nuclear fuel. A number of criteria must be met here. The most important characteristics are compactness and energy efficiency. A spaceship flying to Mars needs to carry a lot of useful equipment, and if all the payload capacity is spent on fuel supplies, then there will be little benefit from such a nuclear rocket engine. Perhaps that's where the interplanetary transport system, which Elon Musk dreams of, will be helpful.